When you draw an electronic schematic drawing, your drawing has two kinds of objects in it. It has symbols and it has labels on those symbols. And those labels are called reference designations. They include a letter which describes what kind of component it is. For example, here you see some R's. Those are resistors. And they include numbers, so you might start with R1, then R2, then R3. Here's a list of common letters designating these components. So for example, R is resistor, C is capacitor, Q is transistor. We can't use T for transistor because T is already used for transformer, so we're using Q, and so forth. Some of these letters get values with them. A resistor is rated in ohms, a capacitor is rated in farads, usually tiny microfarads or picofarads, a battery is rated in volts, an inductor is rated in henries or microhenries. And when you put these labels on your schematic, those same reference designations are used three places. They're shown on your schematic drawing. They're painted on the actual product if it's a big thing like a printed circuit board. And what I've got here is a really old-timey one, but I'm putting it in here because you can see the painting clearly. And then you'll have a parts list where you also list those reference designations. On your drawing, you start numbering the components at the upper left and work left to right and top to bottom. So here, resistor, we start with the first one, R1, then the next resistor, left to right, is R2, then moving left to right, R3, R4, and so forth. That works well for simple schematics. If your schematic is a little more complicated, you might have an upper floor and a lower floor, as it were, different layers. And you might even have something so complicated that you have to break it into modules. Then you list the value, if it's a component that uses the value. For example, here's a resistor that's 10,000 ohms. K stands for 1,000. And we try for just a few digits. Notice how in this schematic these are small numbers. Instead of 2,200 ohms, they wrote 2.2 thousand ohms. So in a minute we're going to look at how to convert these. When you're putting the labels on here, the most important rule is to try to put the labels in a consistent location throughout your drawing, because that makes it easier for your technician who's using your schematic. If at all possible, put labels on top of the components and then try to keep them on top of the components throughout the drawing. If you have to, for some reason, you can put labels under the components. It's better if you can keep them on top, because that's what your reader is used to looking for. But whatever you do, don't split them up. Don't do this like our book showed here with the X through it. And here at the bottom of the slide, you can see why that's not a good idea. Here are some resistors that have been labeled with their labels split up. And what happens is this middle resistor looks like, it's possible that that's 1.2 thousand ohms going with resistor 302. That's actually not correct. That 1.2 goes with the top resistor, but you can probably see how your technician could easily make a mistake if you split up the labels. So we don't do that. Then if you have a component that's arranged vertically on the page, like these are, put the label on one side or the other. And if at all possible, put the label on the right side of the component. That's where your reader is accustomed to looking. So at the bottom of the slide, here is a part of a schematic with an inductor label, 7 henries, with the label above the component, and a capacitor with the label to the right of the component. that's what we're hoping for. This drawing is out of the ASME standard that's called Types of Drawings, and what they're showing you here is that it's useful to put tables on your drawing to help your reader, showing, first of all, here's the highest reference number you used. So when they get to this last number, they don't spend a bunch of time looking around for something that's not there. They know, okay, I can stop. Then also include a table for numbers not used, and that will come up if you've drawn a schematic, then you've done a revision later and removed some component. So when you remove the component, that number is no longer in the drawing, and you put it in this table to alert your reader what's happening. Now let's look at converting units, and don't stress out too much about this slide and the next slide. I'm mostly putting them in here for your reference, but I did want to show you this idea of exponents. So let's look at 10 to the second, or 10 squared. That means 10 times 10. There are two 10s. 10 times 10, so that's 100. Here is 10 to the third. That means 10 times 10 times 10. That means 1,000. Here's 10 to the sixth. That's, there are 6 of those 10s times each other, so 10 to the sixth turns out to be 1,000,000. And then when you put negative numbers in the exponents, those numbers are getting smaller. So 10 to the minus 1 is the same as 1/10, or 0.1. 10 to the minus 2 is 1/100th, and 10 to the minus 3 is 1,000th. Here's a table that I include for you just because it's from the IEEE, the Electrical Engineers Standard, and I just thought you might like to see what these prefixes stand for, in case you need that sometime. Now let's go on to think about converting numbers. So I'm sure you are familiar with the idea that if you have a number with a decimal point in it, that first number next to the decimal point is the ones. The next number over is the tens, then the hundreds, then the thousands. So when we see 5000, we know that that is 5,000. Then the numbers to the right of the decimal point get progressively smaller, 10 times at a time. So that first number is tenths. If this were 5,000.1, that would be 5,001/10. If it were 0.01, that would be 5,001/100th. And here we see 5,000.001. That's 5,001,000th. That last place is thousandths. So let's think about how you can streamline your numbers on your schematic drawings to make them smaller by using exponents. So for example, let's say your number is 5,800, 5,800, and you want to convert that to an exponential form. You start with the first number, in this case that's a 5, and you add a decimal point after that first number, so 5 point. And then you count how many decimal places is it to the end of your number. So counting 1, 2, 3. There are 3 decimal places, so your number is 5.8 times 10 to the 3, or 10 to the third. That means the same thing as 5,800. What if you have a number that's an exponent, like 7.4 times 10 to the third, and you want to know what is that really expressed as a plain number? Well, we still count decimal places, so we'll start 7.4. We'll start with that decimal point right after the 7, and we'll count. If we're saying times 10 to the third, 10 to the 3, we'll go 1, 2, 3. Oops. 7.4 times 10 to the 3 is the same as 7,400 or 7,400. 10 to the third is the same as 1,000. So 7.4 times 10 to the third is 7.4 thousand, or 7,400 or 7,400, however you like to say it. Now what if you have a minus number in your exponent? Let's say you have 7.4 times 10 to the minus third. 7.4, there's a decimal point, times 10 to the minus third, so we're going to be counting backwards. We're going to be counting to the left. So here's 7.4, there's our decimal point, and now we'll count. It's 10 to the minus third, so we'll count 3 places to the left. 1, 2, 3. Our number is 0.0074. There it is right there, 0074. And if you're interested, that happens to be 7.4 thousandths. The 7 is in the thousandth place, so 7 thousandths and 0.4 of a thousandth. Ten to the minus third is 1,000th, or 1 divided by 1,000, or 0.001. So 7.4 times 10 to the minus third, 10 to the minus 3, is 0.0074.